Good afternoon everyone. Myself Dr. Mitali Dugvekar. I am Assistant Professor in the Department of Science, the Bhopal School of Social Sciences. So in the last module we have begun with the topic of chemistry, which is the chemical kinetics, and which deals with the study of the rates or speed of various chemical reactions. In that module we have studied that what are chemical reactions, how is the speed or rate of any chemical reaction determined, and what is the difference between order and molecularity of any reaction. Now in this module I am going to begin with the zero order reaction. What are zero order reactions, how can they be represented, and what is the integrated rate law equation for such kind of reaction. So basically what are zero order reactions? As the name suggests, zero order reactions are those reactions in which the rate or speed of any chemical reaction is independent of the concentration of any reactants used. For example, if I take the example of A plus B gives P, means where A and B are your reactants and B is the product molecule. Now the rate of this reaction or the speed of this reaction will be independent of how much amount of A is taken or how much amount of B is taken. If you increase or decrease the concentration of A and B, it will have no effect on the rate or speed of this particular reaction. Now actually these reactions are called as pseudo zero order reactions, because zero order reactions of this kind do not exist as such in nature, but it can exist in the form like if any of the reactant is in a very large excess, it is taken in very huge amount, so it can be considered as a negligible value. That is why it can be considered that zero order reactions do exist in the form of pseudo zero order reactions. For example, in our body also, the various types of enzymes which are working on any chemical reactions, for example, your digestion of food, without the presence of any enzyme, the digestion of food is not possible. So it can be considered as a part of your zero order reactions. So now if we look at the rate of such kind of reactions, that how do you express the rate or speed of these reactions? We have already seen that rate of any chemical reaction can be expressed, or it is directly proportional to the concentration of reactants, which means that if you increase the concentration of reactant, the rate of reaction will increase and vice versa. So if you remove the constant of proportionality, you will get a rate constant, or the constant which is known as rate constant or velocity constant, and your concentration of A. Also, the rate of the reaction, any reaction can also be expressed in terms of dx by dt, which means change in the concentration of reactant with respect to time, that in how much time the reaction the reactant is decreased, or if we are expressing it in terms of products, with how much time or with the time how much of the product is getting produced. So if I talk about the zero order reaction, now we are going to describe or we are going to derive the integrated rate law equation for zero order reactions. How? For example, first is your A plus B gives products. This is your zero order reactions. A plus B are the reactant molecules which are independent or which are not causing any effect on the rate of this particular reaction. Now since it is a zero order reaction, I will first of all I will have to express it in the form of rate law. So rate means K A into B. Now what happened if this reaction was a first order reaction? Now in case of A or B, the rate of this reaction would have been increased or decreased by the presence of any one reactant, either A or B. But now since it is a zero order reaction, the concentration of this A or this B will not have any effect on the rate of this particular reaction. Now this is the differential form of the zeroth law, zeroth order rate law. For example, A gives products. Now what will happen if I have to write the rate of this particular reaction? What I will do? Minus dA upon dt, and as we have already discussed the reason of this minus sign. This is because as first the reason is that the concentration of reactants is decreasing, that is why we are applying the minus sign. Secondly, what happens that the speed can never be negative, and if you calculate this dA, if there was no minus sign, if there was only positive sign, then if you calculate this dA, it means final minus initial, which would give a negative quantity. So to avoid this negative sign, we already apply a negative sign by default, so that the rate is not obtained in the negative state. Also rate can also be expressed as K, the rate constant, and concentration of A, which is raised to the power 0. Now why this is raised to the power 0? Because this is a 0 order reaction, which means that the rate of this particular reaction will not be dependent on how much amount of A is taken. Now what will happen? I am getting these two equations. Suppose this is my equation 1 and this is my equation 2. Now since both of these reactions are having rate on their left hand side, so we can equate these two reactions. On equating reactions or equation number 1 and 2, what do we get? We get, on rearranging the equation, or we can say we get that minus dA upon dt is equals to K concentration of A to the power 0 according to equation number 2, but this anything raised to the power 0 is equal to 1. So what we are left with? We are left with minus dA upon dt is equals to K. Now on rearranging this equation, what I want that I should obtain only dA on left hand side and the rest of the terms should go to the right hand side. Now what I can do? I can do minus dA equal to K dt. I am doing nothing but I am taking this dt term from left hand side to right hand side. So now since this was in division in the left hand side, as it goes to the right hand side it will become in the multiplication form. So I get this minus dA equal to K dt. Now on integrating, we will perform integration. On integrating this term, what will happen? Negative sign will come outside, minus dA equal to integration of K dt. Now this is a formula in integration. Integration of dA is equals to A, and integration of any constant is equals to the constant only. Now what can I write? I have obtained this term. So the integration of minus dA, I will get dA only. I have transferred the negative from left hand side to right hand side. So here is my negative sign, and integration of K dt will give me K. K is a constant, so it will come outside to the integration sign, and integration of dt is equals to T. Simple. Now what will happen? I will get this particular thing. I have applied the limits from A0 to A. So after the integration of this particular equation, I get A equal to A0 minus KT. Now what I can do? I have to calculate the value of the rate constant, this particular thing K. So in order to achieve this, what I can do? A minus A0 equal to minus KT. So just to remove this negative sign, I will do the reversal of signs in this manner. And on rearranging the equation, I will get K equal to A0 minus A upon T. Now here, what is this A0 and what is this A? This is very important. First of all, this is my integrated rate law equation, or this was what I wanted, where K is the rate constant, A0 is initial concentration of A, that is my reactant molecule, and A is the final concentration of A. So by using this particular equation, I can calculate the value of rate constant for any zero order reaction. Now there is first of all, now if we look closely, or if we look at this particular equation which I obtained, I have just done the rearrangement. I obtained K equal to A0 minus A upon T. What I have done, I have brought this T to the left hand side and I have kept the A or concentration of A on one side, and all the terms I have brought to the opposite side. So I get the equation which is of the form y equal to mx plus c, which is the equation of a straight line. Like for example, if I plot whatever is there in my y, whatever is there in my left hand side, if I plot this on my y axis, which is this axis, and if I plot this x term on my x axis, the value of them m is nothing but the slope. Also the curve which is obtained between y and x will be in the form of a straight line, and the x will be the value of slope, that is this one, and c will give me the value of intercept. So now if I correlate this equation with my equation of the zero order equation, what I get, that if this is my concentration term which is plotted along the y axis, this is plotted against t which is in the x axis. So if I plot the concentration and time, I will get a slope which is having negative quantity, that is slope is equals to minus k over here. That is why this is in a decreasing way. If this was positive, I would have obtained a graph which was in this manner. but since this is negative, that is I am getting minus k, so this slope will be equal to minus k, that is it is reducing. So this is my equation of a zero order reaction. Next, what is important is the relationship between half-life and a zero order reaction. Now what is basically half-life? Half-life is that time which is required for any chemical reaction to complete half. That is, the initial concentration of the reactants must become half. It must become half, and then it will lead to my final concentration, or final concentration is equal to A naught upon 2. Whichever concentration of reactants I took in my first step, if they become half, it will give my final concentration of reactant for the half-life, to calculate the half-life of any reaction. So final concentration is equal to half of A naught, that is half of initial concentration. When I substitute this concentration of A in my term, in my integrated rate law term, what I will get? A equal to A naught minus KT, this was my original reaction. In place of A, I substitute A naught upon 2 or half into A naught, and I will get this T half equal to A naught upon 2K. This is my equation of half-life of any reaction. Now there is one more last thing which is very important over in this case is the unit of rate constant, unit of K, which is generally asked. Like, how can I calculate unit of A? K, I know that rate is equals to K into concentration of reactant. But now since this is a zero order reaction, this value becomes 1. Ultimately, rate is equals to K. So whatever is the unit of rate will be the unit of my K. And we know that rate means what? Concentration upon time. And if I express concentration in terms of grams per liter, and if I am taking time in seconds, I will get what? Grams per liter per second. So this is my unit of K for a zero order reaction. So in this particular module, what we saw about the basic description of zero order reactions. What are zero order reactions? What is the integrated rate law for a particular zero order reaction? The relationship between half-life and the rate constant, relationship between half-life and the integrated rate law which was obtained for zero order reaction, and finally the unit of rate constant. In the next module, I will explain about the first order reactions. I will derive the integrated rate law for the first order reactions, half-life and units of rate constant. That's all for today from my side. Thank you very much.